Okay, we're recording. Thank you all for your incredible patience. My deepest apologies. And I think we're ready to get started, Jeff.
Okay. Yeah, thanks everyone for your patience. I'm Jeff Deems. I'm a research scientist at the NOAA Western Water Assessment and the National Snow and Ice Data Center here at CU. And I'm co-presenting with Joe Barsugli, who I think you all know pretty well. And we will talk to you about some of our recent work looking at the impacts of dust on snow and combined with climate warming in the upper Colorado River Basin. The picture in the background there is from 2009, looking southwest from the high point of our research basin in the San Juan Mountains in southwest Colorado. This is just above Telluride, and I think the dust on the snow is pretty obvious. And I'll dive into some of the processes there. I should, next, there we go. I should note that in addition to all of the entities represented symbolically down at the bottom, there's a whole host of folks that have contributed to a lot of this work, from field observations through remote sensing and modeling. So it's a cast of characters and ever expanding. 2009 was really a wake-up call to us. We saw extreme dust loading on the snowpack in Colorado. And these events, especially the really strong ones, tend to come in with a bit of an apocalyptic flavor. So here's Silverton, Colorado on April 3rd, 2009, with the dust event in progress. Same event in the backcountry near Aspen, same day. And this event hit the entire state of Colorado and beyond quite strongly. Here's the day after that storm. This is me pointing at not dust in the snowpack. That was a pit for avalanche purposes, but you can see 3 major dust layers in there. There's actually a good number more further down, and they show up quite strongly. And note that they grade upwards through the snowfall that followed the initial dust deposition. Similar stratigraphy observed statewide. This is not too, well, let's see, a couple of weeks later down in the San Juan Mountains with a couple of more dust layers up near the surface in that picture. This dust is regional. You may hear we've been battling a PR effort for a long time now with local weather forecasters who like to attribute this dust to Mongolia. And I think it all stemmed back to one event where there was coincident in time. There was a dust emission from Mongolia that made the news, and then dust on snow in Colorado that made the news, and the TV weather personalities put that together inappropriately. So we're fighting an uphill battle there. But we know these are regional dust sources, and we know that from a number of lines of evidence, including direct observations of plumes on visible satellite imagery, back trajectory models looking at the prior history of air parcels that delivered dust, and then the mineralogy and particle size distributions of the dust sampled from the snowpack. I tend to concentrate a lot on Colorado geography for my research on this, but I should note that this is a west-wide phenomenon and indeed a global phenomenon. Here's a strong dust event coming out of central Washington, May 3rd, 2010, blowing straight into Idaho. And I was looking for some pictures from an avalanche forecaster friend of mine in Idaho sent me that year of strong dust layers in the snowpack up there. Here is a MODIS-based remote sensing product produced by Tom Painter and his colleagues out at Jet Propulsion Lab, showing the radiative forcing, or the extra solar absorption due to dust on the snowpack across the Colorado River Basin, or upper Colorado River Basin region. And this is for 2009. You'll notice a really strong impact down in the San Juans, indicating probably proximity to the primary dust source in that case. But the top sub-panel shows the Wind Rivers and other ranges of Sorcas up there in the northwestern Wyoming. So this is definitely a regional problem and not confined to southwest Colorado, like some people tend to infer. We know from some of Jason Neff's work here at CU, from looking at lake sediment cores in alpine lakes in the San Juans and also up in the Wind Rivers, that this is a relatively new phenomenon. We see a jump in dust deposition, about 7 times the background level, coincident with the late 1800s and the introduction of large numbers of grazing animals to the Colorado Plateau. And subsequently a relaxation to about 5 times that background or pre-disturbance level. So this is really an anthropogenic signal here in the broader dust deposition phenomenon. And this is why it's a phenomenon introduced by surface disturbance and the breaking of naturally occurring physical and biogenic soil crusts that form in the dust source regions. These crusts, particularly the biogenic crusts, when fully developed, are virtually impervious to wind erosion. They're very, very resistant to shear, but they're not resistant to compressional force, so that they're easily crushed by, well, in the initial disturbance, hoofs of grazing animals, but today we have a whole wide range of disturbance agents, recreation, development, oil and gas exploration, etc., that continue to disturb and prevent regeneration of these crusts. Here's a well-developed biogenic crust patch. There's a whole host of surface nutrient and water flux components that are affected by disturbance of these crusts, but the primary thing from the snowpack standpoint is the subsequent emission potential. When these crusts are disturbed, we're then dependent on, somewhat ironically, the invasive annual grass health, such that if we get decent rain in the fall and again in the spring, so the grasses can germinate and then grow, that reduces the wind speed at the soil surface and reduces dust emission. However, when we don't get that, then there's just bare soil everywhere ready to blow around. Some work by Jane Belknap and colleagues at USGS Moab looked at disturbed and undisturbed sites. Here's 2 sites with a time series of vegetation cover, and we can see that in drought years where there's very little cover, there's a lot of dust emission, and in wetter years where there's more annual grass cover, there's much less dust emission. And this points, I think, to the potential for dust control through management efforts to control for both disturbance of the soil surface, but also for grazing or disturbance or disruption of the annual grass cycles. We've seen strong variation annually. I apologize, this is only through 2012. 2013 was another extreme year. The top panel showing the number of dust events. The ones that occur in the spring are most relevant hydrologically because they end up on the top of the snowpack sooner. And the bottom panel shows the total concentration. So you can see that 2009 and 2010 were extreme, and 2013 actually edged out 2009 and is to date our biggest dust year on record, at least in southwest Colorado where we're doing these measurements. The reason that the spring storms are most critical is that the dust tends to accumulate on the snow surface through the melt season. It does not wash out with meltwater, so that as the snowpack melts out, each successive dust layer that's buried adds to the layer that's on the surface and absorbs more solar radiation. And that's the mechanism, this decrease in snow albedo. The clean snow reflects virtually all of incoming solar in the visible, which is why it looks white to our eyes, of course, dropping off into the near infrared. And dirty snow, dusty snow, like that shown in the background, is strongly impacted in the visible absorption, such that our eyes are actually doing a pretty good job of telling us just how affected the snow is. we can model this. This is some point modeling showing snow water equivalent through the melt season for 6 years, and this is at our Swamp Angel study site in the San Juan Mountains. The red line showing modeled or simulated snow water equivalent. The black triangles there are manual observations, so our simulation is doing quite well. And then if we go back in and change the albedo to represent clean snow, we get the blue line, and showing much slower melt rates without the dust, and resulting in, on the order of a month to close to 2 months, depending on the year, change in meltout date or snow disappearance date at that site. And if you extrapolate this across the landscape, that is a pretty gigantic influence on the water cycle, and I'll get to that in a moment. We see this in observations. Here's the Beartown Snowtell site in the Rio Grande headwaters in 2009, starting with about the right amount of water equivalent at about the right amount of time, and ending up with the earliest meltout date on record for that site. You can see by the slope of the red line there a very steep meltout curve. Same year, Rabbit Ear Snowtell, this is in northern Colorado in the Yampa River, with, again, very, very fast meltout rates influenced by that heavy dust year. Heidi Stelzer at Fort Lewis College in Durango has also done some work looking at alpine phenology and the green up and flowering of alpine plants under different dust scenarios, and found an interesting synchronization and earlier phenological events with earlier removal of the snowpack due to dust. And she found that this was limited by early spring air temperatures, which has some impacts both in terms of alpine ecology, but also in terms of a broader evapotranspiration balance under a warming climate. So we looked, I mentioned extrapolating to the entire river basin. We did that in this paper in PNAS 2010 using the VIC model and 2 different dust scenarios to evaluate hydrologic impacts of that changing snow albedo due to dust. And we found that under comparing the present average dusty conditions, and this is based on observations 2005 through 2008, so not the extreme dust years, that we are experiencing a 3-week earlier peak in the snowmelt hydrograph at Lee's Ferry compared to the pre-disturbance or pre-1800s conditions, a steeper rising limb which shortens the window over which water management decisions must be made, and about 5% lower annual runoff total from the upper Colorado Basin due to enhanced evapotranspiration from a longer snow-free season. 5% in the Colorado Basin is a big deal. That's twice what Las Vegas gets, 18 months for LA, and half our treaty obligation to Mexico. Some variation in there annually. The bigger years tend to get more snowpack and then have a longer time period over which dust can affect the melt-off rates, and therefore we see the biggest losses in the biggest snow years, which is important because those are the years that we count on to recharge our surface water storage capacity in the Colorado Basin. Some other work by the folks at USGS Moab have done some climate studies related to vegetation cover and dust emission, and suggest that dust emission is likely to increase and potentially increase strongly from some landscapes under a warming climate. So the natural question there is, how will these warming temperatures and increased dust affect dust on snow impacts? And in that regard, 2009 and 2010, those extreme dust years provide us kind of a test case, maybe a taste of the future normal condition. So we created a new extreme dust albedo decay scenario for the model, which results in a much faster decay and lower minimum snow albedo, and ran that through the VIC model in conjunction with climate change scenarios. And here's where I lob it to Joe to talk about our recent work on that.
So I'm going to be talking from, no, Jeff, I think we're going to talk from your slides or mine. Let me just, I guess mine, right? I was going to
yours.
So do I need?
Yeah.
I just handed it off to Joe.
You handed it off to me, and I managed to, in all that confusion, close my PowerPoint, which really Give me just a second here.
Wait a minute.
How come it's not bringing that? Oh, because I did it from my, stupid me, I did it from my laptop. Give me just 1 second here.
And I'm hoping to give you...
Yeah, I'm having my own problems today here.
Joe, I can bring up that presentation if that helps.
Yeah, I mean, why don't you just bring it up if you want to do that.
Okay. So now you got to hand me back.
Here we go.
I made just a few annotations on it, but really, I'm talking from Jeff's, not only work that he mainly did, but his presentation as well. But I got to get involved in this really exciting work by helping to create some climate scenarios to investigate the question of what happens in a dusty world when you have scenarios of climate change and climate warming. And we decided to take a very, very simple approach. So let me just clear off my screen here. So we decided to take a very, very simple approach, just a sensitivity approach, where we weren't going to look at very complicated warming scenarios. We were just going to take an average. For now, we're going to be taking an average of what the climate model said from the CMIP3 models, and use a delta approach on the historic, where we just add the temperature change, or we multiply by the percent change in precipitation. Different at the time, different than what a lot of people were doing with the Vic model, is we actually changed not only the mean temperature, we changed the maximum and minimum temperatures. And I'll tell you what the implication of that is in just a second. But we also changed precipitation. So those are the only inputs to the hydrologic model on the climate part that we're changing. We used average changes over the Colorado River Basin because it's reasonably, small compared to the model grid cells at that time were typically 2 or 3 degrees on the side of latitude and longitude, so therefore the Colorado Basin is really well represented by a large-scale average, the changes at least you get. So we looked at a low change and a high change, a B1 scenario and an A2 scenario. Remember those now that we have the RCPs? Yeah, we still have to remember what these old ones were for a while. And we looked at 2050 and 2100. Next one, please. So this is just a table of the seasonal month-by-month changes in temperature and precipitation. But I'll just summarize that to say you do find in the Colorado Basin a slight increase in precipitation in the winter if you look at the mean scenario, slight decrease in the summer, just very slight. But more important, you see warming, and you see particularly in the 2100 A2 scenario, you see quite a bit of warming in the summer. You do see differential warming in Tmax and Tmin, and that's really important because the way Vic is being run, it takes very simple climate, Tmax, Tmin, and precip, and it infers the radiation and humidity using the MT-climb empirical relationships. So that means if you have a larger diurnal range in temperature, it typically infers greater insulation. It thinks it's clearer, for example. If you have a lower Tmin, then it infers that it is drier. It also computes aridity factors. I was hoping Jared Euler would be on this. He did some work talking about the limitations of this approach. But for this kind of sensitivity study, this approach is quite valid. You may want to ask some questions about the actual numbers, but again, we'll talk about that at the end. So once again, we run 1915 to 2003, and we with historic moderate dust forcings, and then we perturb both the dust and the climate factors. So next one. This is what I was going to skip in mine, and I think I'm going to skip it. Let's skip that one in interest of time. So here we have the set of hydrographs in the historic situation. This alone just shows the effect of dust loading. Blue is as if low dust, moderate dust in red, and the extreme dust scenarios. And what you can see is, pretty much a linear shift in the peak, backwards in time, by as he was suggesting, up to more than 30 days, more than a month, sometimes almost 2 months, and clearly an effect on volume, which we'll show in the next slide. Hit the animation here, because now let's show what happens when you actually look at the future runs. What you see is basically the volume goes down, and there's an even greater impact on timing. And we'll be summarizing those a little bit later. Let's go to 2100. This is, once again, you see, things volume being very visibly affected, timing as well. So you have dust and snow both affecting timing, and to some extent volume, and we'll see what happens when we look at that when we look at some of the numbers later. Next slide. So the question on total runoff volume, the top is just the historic simulation of, in this case, million acre feet, year by year from 1915 through 2000. I forget, it was the number 2006 we did it through, right? 2000.
I think it was 3 for this simulation, 2003.
2003 for this simulation, yeah. And the middle panel, pardon me. So the blue curve in the middle panel just shows the change in total runoff, again simulated year by year, with only a change in the dust. And you can see, of course, the year-by-year fluctuations are very similar. You see high years and low years. But you see an offset, which of several million acre, well, a million, in that case, about 1 million acre feet, a little bit less. The black one is the extreme dust, and you can see that there's an offset, but not nearly as much, actually. The banded curves show the changes for when you have low, medium, and extreme dust in 2050 and in 2100 down below. And you can see that, again, large effects particularly in certain years when you actually have low flow. You can have a really, really severe effect on the volume. And we'll talk a little bit about mechanism, hopefully, before the end of the hour. Let's go on to the next one. So this shows timing, and timing shows a much more organized shift between all these different scenarios. You see, basically, that the more you force it either with dust or with warming, the more the timing shifts. So let's go to the scatter plot, which I like really better. So this summarizes in percentage change on the right and in days shift in the center of mass of the hydrograph on the left, the various different runs that we were showing there. So on the left, you see, let's look at the round circles. That's the historic run with different levels of dust. You just see pretty much of a linear shift. Clean on the left, moderate in the middle, which is our baseline, and extreme on the right. You see that linear shift occur no matter which warming scenario as you go down to the triangles and squares that you look at. You see a linear shift due to dust. You also see a whole linear shift pardon me. What you see is pretty much a monotonic shift due to, if you look at within each scenario, you see the warmer the climate run, the earlier the runoff. And you see some of these effects are on the order of a month in the extreme case here from the moderate case. And the difference between the two will depend on which warming scenario, which dust scenario you're in. So the question is, on the right you see runoff volume. You see something very interesting. You see the extreme dust case not really affecting volume much more than the moderate dust case. And so when you talk about mechanism for this, at least the mechanism that was found to reduce runoff was that you actually expose the ground. You have more evapotranspiration during the spring season because there's simply more exposed area that's wet from the melt, and that in turn leads to an overall loss in the yield of the basin. It seems like that's not affecting the high dust scenario pushes the melt so early that the temperatures just aren't there to support the evapotranspiration and the plant respiration going on. So extreme dust pushes the hydrologic cycle early, but there's just not, at least in the model, there's not enough in place, not enough temperature, not enough conditions. The conditions are not in place for the plants to do their work, basically, or for the bare soil to do their work, for that matter. So under a warming climate, what you see is that the dust actually is able to do its work earlier, at least with the moderate dust case. So that's why warming and dust do act synergistically to push down the yields, because the warming will allow that ET to take place in a dusty scenario. But within each warming scenario, going from moderate to extreme dust still pushes you past the limit where you're actually having any sort of ability to have more evapotranspiration. And as Jeff was mentioning to me earlier, when you get in the really warm scenarios, there's rain during the winter, accumulation season is very, very limited. There's a lot of rain during the fall, in other words. You get a lot less overall accumulation, and that affects, and a lot less accumulation of snowpack. There's more rain with more immediate runoff, so the whole situation becomes distorted as you get to 2100 in the high scenario. Next one. I think that's the end of it. I hope, it's noon now, I was hoping we could have a little time for questions and discussion, maybe some implications for North Central, or just, speculation. So we put a sort of round robin questions. Anybody who has any thoughts, interests, questions about how this might be applicable in other places?
I would just say thank you to everybody who stayed and joined. If you need to leave, thank you. But if you can stay, we certainly have the phone line, so please do, and we can have discussion.
This is Diane Dubinsky. I just wanted to say I'm doing an experimental snow removal project in Wyoming, and it doesn't have that many replicates, but it's interesting to think about another potential avenue for testing a variable, which would be to experimentally add dust.
Yeah, actually, that's an interesting point. The Heidi Stelzer's work that I showed one plot from earlier, she did a number of different plot treatments, actually within the field of view of the image that's up there now. She both removed dust, because it was a moderately dusty year that she was working in, also added dust, and then she also did some fabric plots where she stretched out some landscape fabric, black mesh, over a 30 by 30 plot, and that had the most extreme impact, of course. But she was definitely looking at different methods of changing the snowpack ablation rate.
Yeah, I'll take a look at that article.
The ecological response?
Say that again, Joe?
Yeah, that was that paper.
Yeah, you're looking at, so Dan, you're actually looking at the response of the plants.
Yeah, we're looking at plant community responses and phenology responses, timing of flowering, timing of emergence, and things like that.
Whereabouts in Wyoming?
It's about 7,000 feet elevation in the Tetons. So it's a low elevation meadow, sagebrush meadow. But it's interesting to think about this because, you know, it'd be interesting to make the comparison between the high elevation sites and the low elevation sites.
Diane, I'm eager to talk more about this with you.
Is that Geneva? Yeah, sure. Feel free. I have a little blurb about it on my website, but we have not published it yet. But basically, we're doing a pretty good simulation, I think, of moderate changes, because what happens is the snow is removed a few weeks early, and we also have a warming chamber that we've added to some of these plots, and so we're modifying the nighttime temperatures particularly. It makes a very small difference, but probably significant in terms of the days where you get frost on an emerging plant, or the time when a plant that's already just come out experiences freezing temperatures.
I was wondering that myself. You know, in the sagebrush areas, the lower elevation of the higher elevation of the sagebrush, where you do have snowpack as part of the cycle. I don't know, Bill, are you still on the call as well?
Unfortunately, I saw that Bill just had to leave, but Joe, I was having similar thoughts related to the work about seedling establishment, for example, in sagebrush species.
Because it's just if your snowpack melts off quickly, and you have really, I presume that would make for drier periods in the summer as well.
Oh yeah, yeah. We have soil moisture meters in the soil, and you can see the response throughout the entire growing season of having a drier soil condition.
So that's really an interesting connection here. So I don't know, Jeff. I mean, there are these satellite products that attempt to map the whole dust effects. Is that something, Jeff, that Tom Painter is producing regularly for public consumption?
He is. I can't tell you offhand how to access them, though. I'm not quite sure where they're stored. I know one of his products is hosted here at NSIDC, but I'm pretty sure the dust product is not. So I usually just get it straight from him. So
yeah,
I'm not sure.
If you can bring some of that into the whole, North Central database as well.
Yeah, that'd be interesting to know how much of an issue it is. I mean, obviously it's pretty significant where you're collecting these data that you just presented, but it might be a more subtle situation but still having an impact in some of these other places.
Well, at least our point modeling, which was conducted at one of the energy balance sites, like is shown right now, showed that even in a moderate or by our new standards a low dust year, still has a several weeks impact on snow disappearance date.
Yeah.
And that can be amplified by in the bigger snow years. You have a longer melt season over which those two melt curves can diverge and end up with different dates. So, like I said in the VIC modeling segment, that we depend at least at a broader scale on those big years to recharge things, and if that's where our biggest impact is happening, we're not getting the recharge we're used to.
I think another interesting component is you'd mentioned dust sources, and the larger scale to spot like a dust event, but then I think it's interesting coming up the whole Rocky Mountain range where we have significant energy development, that there could be potentially significant local sources, even if events were smaller. And I'm thinking, for example, like the Wind River range just south from the Tetons, where there's extensive energy gas field development to the west.
Yeah, good point.
And southwest Colorado would have similar situation.
And Jeff,
yeah, that's true. And then there's the
western slope of the Tetons, right?
Say that again? I'm sorry.
I think Jeff was mentioning to me some events that hit the western slope of the Tetons.
Well, I'm not quite sure how far over that Washington event went. It's certainly within range atmospherically, but I know that Central Idaho got strongly affected by dust from that 2010 event. There are other more local sources in the Snake River Plain, other dryland agriculture areas that, with the right conditions or the right crop, or lack of crop, could be ready to emit dust. We're seeing an interesting transition in southwestern Colorado of some dryland agriculture from food crop to biofuel crop. And apparently those crops are fallow in the springtime when those new crops are fallow in the springtime when we get most of the hydrologically significant dust events, and therefore have become a dust source, whereas under food agriculture cultivation they were not. So that's another interesting energy connection there.
Yeah. Can you too send us a couple of these papers that you've done that relate to this
Sure.
presentation you just gave? Yeah, that'd be great.
Yeah, happy to.
Okay. I have to check out and do some other things, but that was really exciting, so thanks for presenting.
Yeah.
Sure, thanks for the opportunity.
And I hope we can be more involved and just connect again with what you're doing, Diane, and make sure that we all stay informed.
Yeah, that'd be great. I don't know when we're going to see each other at a meeting in the near future, so Geneva, let us know if there are some opportunities for that. But this is great. I mean, having these webinars monthly is a good thing, and having the chance for people to actually interact a little bit informally is great.
Yeah.
Okay,
yeah,
thanks
so
everybody.
Thank you so much for staying on.
Sure.
I feel it low attendance. It was very valuable, and I'm thankful that we were able to record it.
Well, let's send that out to the group, and that'll be great.
Okay. Best, you guys. Thank you.
Yeah, thanks very much.
Great, thank you again.
Thank you all.
Okay. Bye-bye.